Welcome to my second session in my track about financial option theory with Mathematica. Today we will be deriving and analyzing the eponymous Black-Scholes PDE partial differential equation, and we will relate it to the one-dimensional heat equation. They are very closely related, and we will transform the Black-Scholes PDE to the heat equation and then for a round trip go back from heat equation to the Black-Scholes PDE. The BSPDE is the crucial PDE in computational finance. It is the most prevalently used, and it's the foundation for all the other PDE-based derivations that we have. The Black-Scholes PDE applies to many financial derivatives, not just the options. We will be focusing on options in this track, but it applies to many other financial derivatives as well, futures, forwards, and even when we don't use the Black-Scholes PDE, for example, the Fokker-Planck PDE is sometimes more useful for futures on interest rate derivatives, then Black-Scholes still provides the great foundation and the PDE to study all the items derived from it in order to understand a more general way to handle the pricing of financial derivatives based on differential equation theory. Because differential equation theory provides a wealth of tools that we're getting directly from calculus, and it allows us to analyze many PDEs. And the BSPDE is so prevalently used and a great starting point for many other derivations later on. So let's jump into it. Let's derive the Black-Scholes PDE. We start with a very simple stock price evolution that follows a simple SDE, and we've used this model before. I immediately start with a footnote. As before, both the appreciation rate minus dividend rate as well as noise increase with the stock price ST, right? So you see S of T is multiplied with the entire expression, right? It's multiplied with everything on the right hand side. And we have the appreciation rate on the right hand side, and from that we subtract the dividend rate, and I'll explain this in a moment. And we have a noise term, we have random noise here that is based on Brownian motion differential, and we multiply this with the stock price at time t. This is a realistic assumption because we can assume that the appreciation increases with the stock price, and we can assume that the noise in the stock price evolution increases with the stock price itself, and an initial condition. So here we have the appreciation rate and sigma as the appreciation rate and the volatility. This is as before, and we note that here they're both time and stock price dependent, right? You see that A depends on T and S of T, and so does D0. The dividend rate also depends on time and the stock price at point T. And also sigma depends on T and stock price of T. As I said, D0 is the annual dividend rate, and I need to spend a few moments on explaining why we're using a dividend rate here. Dividends are, of course, not paid as a rate. Dividends are paid in fixed, usually predetermined time intervals, such as monthly, quarterly. Some companies pay semi-annually. Some pay annually, but mostly dividends in the United States are paid quarterly. But they're usually not very high, and the company tries to maintain a constant dividend policy. After all, a dividend is somewhat an interest rate equivalent. So when you have cash in the bank, then you earn interest, and in order for a company to get your money to buy the stock, they have to pay you a little bit of an equivalent. Why else would you buy the stock? So they have to pay you a dividend, and that way they make it attractive for you to buy the stock. Instead of having $100 in the bank, well, then maybe buy the stock at $100. But if you just buy the stock and it has no yield, then why should you buy the stock? And that's why many companies pay a dividend. You can think of it as an interest rate equivalent. And the companies therefore aim for a dividend rate that is more or less consistent with the general interest rate level that a country has. At higher interest rates, the dividend yields go up. At lower interest rates, the dividend yields go down. But they're usually not large amounts, and that means that it's okay to convert these dividends into a yield, an annual yield. They're usually paid as fixed amounts every quarter, and they are usually not showing very jumpy or irregular behavior. So we consider them an annual rate for our pricing purposes. And an important consequence of a dividend payment is that a stock price will immediately decrease by the dividend amount when it goes X. And that is called going X dividend, or sometimes simply the dividend goes X. Yep, that means X dividend. And that means that point in time when the company pays out the cash. A dividend payment is a cash payment. And at that moment, the stock goes X. And that means that the money goes out, and given that a share is really a share in the total assets of the company, that's why it's called a share, because you have a share in the total assets of the company, and the company now pays out millions in cash, well, then that means that the stock price decreases by an appropriate amount. And that means that we are subtracting the dividend rate here from the appreciation rate. It stems from the ownership of the shares. The money is no longer there. It was just paid out to the shareholders, so the company doesn't own the money anymore. And due to that, the company value has decreased by the amount equivalent to the number of shares times the dividend amount, because the company just lost that amount of cash by paying it to the shareholders. All right, so that's why we have to keep in mind that we have to subtract the dividend rate. Okay, and in the following we will derive the BSPDE by using a put, and an equivalent derivation could be made with a call, but it's easier to understand it for a put. Presumably you're buying a put because you want to hedge against losses in the stock price. When you have the stock in your portfolio and the price of the stock goes up, then you probably don't have a problem with that. But when the stock moves down, then you want to have some kind of insurance. You want to hedge against that. And a put is sometimes called a protective put, because we can now earn on the put what we're losing in the share. So based on the ratio, how many puts we buy, then we can either completely eliminate the loss, or we can make even a little bit more money, or we can make less money on the put if we buy less puts than we would have to buy in order to completely hedge it. Okay, so that's why it's usually easier to understand the hedging with a put, because usually you are long the shares and you want to protect against a loss in the share price, not an increase in the share price. Yep, so presumably you have the put to hedge against the loss in the stock value. So that means we'll assume that the portfolio of the shareholder consists of, if we have a single put option and a yet to be determined number of shares, we will call that a delta in the future, and a cash account. That means our portfolio value, and we call that X of t, is now the value of the derivative minus a ratio of shares plus cash. Okay, so let's look at how the evolution for that would develop. So we are interested in the differential on the cash amount, right? The differential of C. And this we start out with the interest rate times the cash amount over time, right? Because we get interest on the cash and we're taking differentials. So here we have to multiply with our differential for time, and that is dt. So this is the change in the interest we earn on our cash amount. That cash amount is the amount of money that we have deposited with the brokerage, but we didn't buy anything with it. We didn't buy stocks, we didn't buy calls or puts. And we need an appropriate hedging amount, delta, that we multiply with the shares and the dividend amount, right? The shares times the dividend amount is the dividend that we're getting, the dividend rate, right? Dividend converted to a percentage times the shares, that's the dividend rate that we get. It changes over time, so we have a dt, and we need to have the appropriate ratio that we don't have yet, but we're setting it up in this equation because right now this equation is just an ansatz. And then we have to look at the stock price itself and the change in our ratio, and note that here we have to add dt because we have to make the transaction in shares at a later point, right? Presumably now the market changes now, it goes up or down, and then we have to make our stock market transaction. We don't know what the future holds. So when the market goes up, then we want to sell some. When the market goes down, we want to buy some. So we have to look at the stock price at the point t plus delta t. This is important. Yeah. So this is the differential for cash that we have when we're setting up the stochastic differential equation in this way. And as I mentioned, this already includes interest rate times cash, and the minus delta t is now our ratio. It's for the dividend that we are receiving during the period delta t, our time differential. And we need to add dt because we need to wait for one time unit, for one differential time unit, before we can make a transaction. We first have to see the move in the stock before we can decide whether or not we want to buy or sell. First, the move has to happen. If the move hasn't happened yet, we don't know yet if you want to sell or buy or do nothing. Right? So this is important to note, that here we have to look at t plus delta t, because we can make this observation, we can make this decision only at time t plus delta t. All right, and next, after several transformations that I'm skipping here, and please have a look at page 88 in the Stoyanovich book, I spare you the details at this point. We are arriving at this SDE. This is the differential on the portfolio value, right? And keep in mind, portfolio value consists of our stock portfolio, derivatives portfolio, plus cash portfolio, right? The cash amount deposited with the brokerage. So it's the time change in our financial derivative plus several other terms. Note that we have a second derivative by stock price here for the financial derivatives, and a few other terms. Okay, so I also want to emphasize at this point that this formula is valid for any hedging strategy, delta of T and S, and any option pricing formula V of T and S that is used in the market. We didn't specify this yet. We didn't say if this is European, if this is American, if it's even an option. It could be a future, it could be a forward. This formula is still entirely generic, and no hedging strategy or option pricing formula has been specified at this point, right? At this point, we don't even know what financial derivative we're dealing with. We're calling it V, capital V. And we just say V depends on time and the stock price. Okay, so at this point, I want to emphasize already that on the right hand side we have a first derivative by time and a second derivative by space. This will become important later when we are dealing with the heat equation. Okay, and now our question becomes, is it possible to design a riskless hedging strategy? where do we find the risk? What is the risk in this differential process here? And the differential of our total overall portfolio value. Where do we find the risk? So an obvious place to look for risk is in ds of t, because it contains the Brownian motion term that we have. And see our first formula above that we have on this page. So the differential in the Brownian motion, and this is the randomness, is our risk source here in this case. But even if we eliminate the Brownian motion, we still have risk. What is the other risk? Well, the stock price itself, right? The stock price itself goes up and down. So we have to start with the hedging strategy where we are saying our change in the ratio delta of TNS is the stock price dependent change in the financial derivative. This is the first spatial derivative of our financial derivative. A lot of derivatives here. All right, so it is dv by ds. And I think this seems natural. It's also intuitive that the hedging strategy should be the first derivative of the option price with respect to space. And space here means the stock price. And later when we talk about the risk parameter, this will become known as the delta of the option. And I'm already using the Greek letter delta here. Okay. So with that, and after further function transformations, which again I'm skipping here at this point, have a look at page 89 in the Stoyanovich, we are getting this SDE. It is a bit transformed, and I'm not explaining the derivation, but this is what we get at this point. And again, note that we have a time derivative here, and we have a second derivative by space multiplied with the square of the stock price, and other components like rate, times, cash, and so forth. And again, this still holds for any option pricing formula or algorithm, right? So we notice that the risk here is vastly reduced, but it is still present because we still have the stock price. We can see that we don't have any Brownian motion in this anymore. There is no more dB left in this equation, but we still have the stock price itself as a random process. So to completely eliminate the randomness, we need to require that the portfolio earns us no more and no less than the risk-free rate. This is the equivalent that we would expect. We want interest rate on the total portfolio value, right? Otherwise, we think it's not fair. The portfolio should earn us what we can earn on the bank. So we multiply R with the portfolio value and we take differentials. And with that and substituted, we are getting this partial differential equation. And you will see now that this is the eponymous Scholes PDE, and it is now a PDE. You will see that this is no longer an SDE. We don't have any differentials, right? This is now a PDE. We don't have any dx or any, what did we have before, dc terms in this. This is now a full-fledged PDE. And now let's say that we're talking about options, right? We now want to impose the payout profiles, and in PDE speak that would be called the initial or terminal conditions. And we use these two formulas for our call and put terminal conditions or initial conditions based on this perspective that we have. We use capital T for the expiration. So these are the terminal conditions that we have for call and put options, right? That's the maximum of 0 and K, the strike price minus the stock price for the puts, and for the calls it's the maximum of the difference between S minus between the stock price and the strike, and 0, that is for the calls. Okay, so let's do some immediate observations that we can make about this PDE. The PDE that we have here, the Black-Scholes PDE, is linear and it's backwards parabolic. And this can sometimes be a problem because backwards parabolic systems are not generally solvable. In this case we can. The BSPDE can be solved also backwards, but in general the backwards problems cannot always be solved. Whether or not they can be solved, and sometimes they're also called inverse problems, is a lot of complicated theory that is still vastly unexplored. It is a real big body of theory, very complicated, in order to make statements about whether or not a backwards problem can even be solved. And I think it's easy to understand why such systems are not generally solvable. We can imagine flows that are of a nature that is impossible to meet prescribed certain terminal conditions. An airflow or a liquid flow. And in the case of our calls and puts, it is so simple that we don't really have an issue here. But in general, we have to emphasize that not all of them can be solved. But in our case, they are sufficiently well behaved. They're sufficiently benign, and I intentionally leave it very vague at this point. You see two straight lines here for the call and two straight lines for the put. That is really not too hard, right? You will remember these payout profiles from the last session. So we don't have any actual problems here. And I emphasize that the terminal conditions are the only parts in which calls and puts differ. It's the only thing that makes them different. Other than that, calls and puts are the same thing. Okay, note that the Black-Scholes PDE degenerates for S towards 0, which implies that no boundary condition is needed, nor that we could even apply one. At S equals 0, then we cannot even apply a boundary condition even if we wanted to. If the stock price is 0, we don't really have a company anymore, right? It means that all the assets are gone. And if a company has no assets, there is no company. And next, we also want to note, a lot to note here, that the appreciation rate A no longer appears in it, right? We don't even have it in it anymore. Which means that the fair option price does not depend on the appreciation rate of the underlying stock. It strongly depends on the volatility, but not on the appreciation rate. You will see that we have no A left in this equation. And that intuitively makes sense because all the investors' expectations and anticipations of the future appreciation of the stock, they even out. We're getting some aggregate market process that means that we don't really have any appreciation rate in the Black-Scholes PDE. If there were one, then there would be a clear market indication, so then perhaps everybody would buy and that would bring the stock up, or everybody would sell, that would bring the stock down, making everybody a loser again, right? You don't want to buy in a climbing market, you don't want to sell in a declining market. So clearly we have a consequence here. The perceptions and anticipations of the shareholders about the stock's appreciation are unimportant for option pricing. You may have an individual one, and we will talk about pricing based on individual appreciation rates later, but for the market pricing, they're totally unimportant, right? They're very considerably among the traders and investors, and one can argue that precisely because of these different perspectives, we even have trades, right? If I didn't think that the stock would go up, why would I buy it? Put it on the bank. If I didn't think that a stock would lose in the future, why would I sell? Keep it. It keeps the value for later. So we have these trades because people have different perceptions about the future development of the stock but it still means due to the aggregate market principles, we don't have the appreciation rate in the Black-Scholes PDE, right? It doesn't matter, it's irrelevant for the PDE. So the volatility is much easier to observe, and there is much higher level of agreement among the traders about the volatility levels, and we will have sessions about that later on. Okay, so that brings me to the heat equation. It is the closest relative to the BSPDE. However, the heat equation also exists as a forward parabolic PDE, not just as a backwards parabolic PDE, and the forward version is used much more commonly. Time usually goes forward on planet Earth, so it's easier to use the heat equation in the forward version. People generally start with a known temperature distribution, so now it's an initial value problem, not a terminal value problem, but it's an initial value problem. So we start with an initial known temperature distribution, and then we see how these things diffuse over time. The heat equation also exists in several dimensions. We are only looking at the one-dimensional here. The heat equation in principle exists in n dimensions. So the heat equation is the predominant equation used to model diffusion processes. And the diffusion processes are special cases of the evolution processes. So in diffusion processes, the dominant equation is the heat equation. So we're writing it down. The forward one-dimensional heat equation with x denoting space is this equation here. And you will see that we are talking about a second derivative by space and a first derivative by time. It basically means the second derivative by space is the same as the first derivative by time. That's what makes it the heat equation. Okay, and I skip the theory here. I just give you the formula. There is a formula, an integral formula for the solution of the heat equation. We have no boundaries here. There are no boundaries. The domain is infinite in both directions. So we have the solution of the heat equation u of t and x as this integral, where we have time as the independent variable on the right hand side, and we have x as the independent variable for space on the right hand side, and it occurs in the integrand. The integration variable is an unimportant variable xi here. We don't care what it is because xi disappears in the integration. But note that we have the spatial variable and the time variable in the integrand, and we have the time variable in the factor in front of it. And also notice that we have a Gaussian Bell integrand here multiplied with the payout profile. This is the way to think about the heat equation. We start with a payout profile that we have as an initial condition, and you will probably see that better in a few moments when we are plotting these. So you start with an initial profile, with an initial function that we have here at time 0, right? We're going forward in time in this case, so we start at 0 and then go forward, and we multiply this with a Gaussian Bell integrand. You will remember from the last session, e to the minus, and now comes the independent variable squared, was the integrand for the Brownian motion, for the normal distribution. This is how we do the Gaussian bell curve. Okay, I have summarized here. The integrand is a Gaussian bell curve multiplied with the terminal condition, or sometimes initial condition, doesn't matter. And the whole integral which performs the expectation operation is normalized with the factor in front of it. Right, here this is the normalization factor. And yes, I also emphasize that with this integration we also have an expectation operation. Right, when we were using at the discrete cases in the last session, we were using mean. The expectation in the discrete case is the mean, for example in arithmetic average. But in the continuous case, we do that with an integral that performs a smoothing operation and gives us the expectation here. So we're also getting an expectation. Okay, so let's look at some special cases that we have for particular terminal conditions. So in this case, let's just leave out the payout profile or the initial condition or the terminal condition. And in this case, when we're integrating this, then we're just integrating the Gaussian-Bell integrand and we get 1, which actually means we have a distribution, and this is the normal distribution, right? This is exactly the normal distribution that we've seen last time when you integrate this from minus infinity to infinity and you get a 1, you have a distribution. And another example, let's multiply with e raised to the power of the integration variable. In this case, it's s. This is equivalent to shifting by t. We start with e to the s, and what do we get? We get e to the t plus x. We're basically shifting it around. We are shifting the function to the right or to the left. And let's look at this a little bit. We can change the, I use tr when I want to look at upper or lower bounds. We can see that we have like a curved piece of paper, and over time this decays. Again, the heat equation is a diffusion process, which is an evolution process. So we're getting this time shift. You can think of this as shifting the exponential function right or left. How about we start with the sine function as initial condition? And in that case, we are getting a solution that looks like the sine function that will decay with the exponential function. It's simply a time decay, and we do that by multiplying with e to the minus t of the sine function. So let's look at this graphically, and I think sometimes a contour plot or density plot says more than a three-dimensional plot. You see that here we start with the sine function. This is our initial condition, and over time the sine function decays. We can still maybe see a little bit of a sine nature here at the end, but it's almost completely smoothed out. And again, let's look at the plot at a time point very close to the initial. So you see, when I set tr to a low number, there wasn't much chance for a decay to happen. So we see a valley here and a mountain ridge here, and that is reflected in the contour plot. But if we let time progress, we see that things smooth out, things diffuse away, and everything becomes a bit of an average or a smooth level surface where there are no longer any major ups and downs, not any major differentiations. Okay, let's take a Gaussian-Bell as an initial condition, right? So we are multiplying e to the minus s squared with another e to the minus s squared, all right? So we're diffusing with the Gaussian-Bell over time, but our initial condition was also e to the minus s squared. That is the Gaussian-Bell integrand. And with this formula, let's look at some plots here. And here we have the same story. We start with a Gaussian-Bell at 0, and over time it diffuses away, right? We start, let's make it a short time. We see we have this mountain ridge here, and over time this simply diffuses away. This is what the heat equation does. And let's look at some jump discontinuities. They also fade away over time. They all fade away over time. That's what the heat equation does. And in a jump discontinuity, maybe we can see it clearer. So far I've used smooth functions, right? But we don't have to keep it with smooth functions. Maybe we see it better when we are looking at discontinuous functions here. So we start with this gate. This looks like a gate, like a door that we get in, and initially we have this gate and not much diffusion happened yet, but then over time things diffuse away. Okay, so how about another jump, this piecewise? And with this piecewise, we're getting a function that looks very close to a delta, right? This basically represents the delta of an option. We'll see this later. Or it can also be the payout profile of a digital option, also called a binary option, once we are looking at the exotic options. But here as well, we see that we have, to one side we have 0, to the other we have 1. So we have this kind of cliff here, and it diffuses away over time. So this is the way the heat equation works. You start with an initial function and diffuse away. All right, so next let's develop the heat equation from the Scholes PDE, and then let's do the round trip by going in the opposite direction. So we start with our famous equation, the BSPDE, and we now have to do several substitutions. So we introduce substitutions A and B, and with that we are defining this equation. So I call it BSPDE 1 because we will now have several versions of this equivalent transformation for the PDEs that we are going through. So I'm introducing A and B here for substitutions. They make some of these substitutions and transformations that are going to come much easier. But we can always back substitute. So if we use R minus D0 for A and R, the rate, for B, we get the BSPDE black. So I'm not cheating here. If we are making these substitution on BSPDE, A becomes rate, interest rate minus dividend rate, and B becomes R, and R becomes a function of time, and sigma becomes a function of time and stock price again, then we're getting our Scholes PDE back, right? But for now, these A and B substitutions make it easier for us. And we also define symbols, terminal call and terminal put, for our terminal conditions. We store them away in tcall and tput. Next, we make more substitutions, and they are motivated by going to a logarithmic stock price. I had touched on this before in the previous session. This is called the moneyness. Moneyness is the ratio of stock price over strike, and we want to deal with logarithmic stock prices here for our Scholes theory. Time, we want to rescale with the square of the standard deviation, and we also want to go backwards in time. T is the expiration, so if we start at a point T in the future and we are subtracting time from it, we are basically going backwards from a point in the future towards now. So we are doing this transformation, and stock price now becomes X. This entire equation still represents space, and we are transforming time into tau. T becomes tau, and additional substitution. So when we apply the substitution here, I call it BSPDE 2, we are replacing the financial derivative value with the substitution and apply all these other substitution here that we just defined. We're getting this equation. And I want to point out already that we already have something here that looks a bit like the Scholes PDE. We have a first derivative by time and a second derivative by space. We're not completely done yet. We still have an expression v here outside of this difference here in the parentheses, but we're making progress. Also here is a view. So We're not quite done yet, but we can see that we are beginning to get something that resembles the shape of the heat equation. And we also have to apply our substitution to our terminal conditions. They now become initial conditions. And we perform some further substitutions here. And I define now a BSPDE version 3. We get now this version of our transformed PDE. We still have this difference here, but we still have our U outside. Right? We have a U here, we have a U here. We are still not quite done yet. But we can make big progress if we now create new initial conditions by extracting U from the last version here, that is BSPDE 3, and the initial conditions. So we have to make some additional assumption now. We assume the strike is real and larger than 0. It makes no sense to have stock price strikes that are negative, and the exponential function is always larger than 0. So that means we are allowed to perform this division. We can take both sides of the equation and divide by e to the x alpha times k, right? E to the x alpha is larger than 0, k is larger than 0. So we are performing an operation here that is permitted. So these are our transformed initial conditions or terminal conditions. But that means next we need to find alpha and beta so that the BSPDE 3 is reduced to the heat equation. And we can do that fairly simple if we are setting up our parameters in a way that they match. You see that we have k times e to the beta tau x in both of these equations. And we solve the problem if we are setting them to be equal. Then we can eliminate these terms in our BSPDE 3. And it's really not all that hard to do that in Mathematica. I think solve doesn't even get out of bed for us to solve that. We have our alpha here and we have our beta here. Right? In no time Mathematica was done with solving this problem. But now if we are applying that substitution, right, the result of the solve I store on alpha beta sub, we now apply that substitution. What do we get? We are now getting an expression where we have our difference in the u's here, right? The second by space minus the first by time, and no other u's occur in this. We still have independent variables. We still have our tau here, and we have an x here, but not u, right? So we are actually okay dividing by this now, right? We're almost done here. We have almost our heat equation here. Everything around is just parameters, constants, and variables, but not the function u itself. Right here it becomes quite apparent now that we have the heat equation. So we also substitute that away, and we also need to do that in the terminal conditions. And here I use a substitution for the max function. We want to factor out a times b when we have a times the max. Right? When I have a times the max of 0 and b, that is equivalent to saying the max of 0 and the product of the two. And I want to factor out the expression that we have inside the max already. So I do this in one step. And if we do that, then we can see that we now have these expressions inside the max. Right? We have our expressions involving a and sigma, x, and our transformed strike k in the terminal conditions. So let's play with them a little bit, and we can see that they already look somewhat similar to the call and put payout profiles that we would expect. We can change a here, we can change the standard deviation sigma here. It can get a bit wacky for the puts. You can see that I can generate some fairly wacky functions here just by changing a and sigma. Right? Looks very different compared to the calls. Okay, so here they are dependent on a and sigma. And well, I don't want to beat a dead horse, but we already saw the heat equation in disguise, where we have this difference here multiplied with something that depends on independent variables but not on u. And outside of this parentheses, we only find several parameters that contain constants, variables, but nothing involving u. So we can divide. And if we do that, we apply to both sides a division by e to this expression times k times sigma. Then we suddenly have the heat equation there. Right? We're done. Voila. It's legitimate to perform this division here. Okay, so what we just did was we transformed the Black-Scholes PDE into the heat equation. We needed to keep track of several substitutions along the way, and we also needed to transform our initial condition into terminal conditions. Okay. Now next, let's do the return trip. Let's start with the heat equation and transform back to the Black-Scholes PDE. So let's recall the terminal conditions that we had. You remember we just saw these formulas for the call and put terminal conditions. Let's define two shortcuts. We take only the inner expressions here and call them c of x and p of x. Right? You see these expressions here are the inner expressions in these two max expressions here, and I point out they only differ by the sign. Right? There's nothing different here between those two other than the sign in front of it. And we next compute the solutions of the heat PDE as we did above. We multiply the Gaussian Bell integrand with the terminal conditions. This is exactly what we've done before to solve the heat equation. We take the Gaussian Bell integrand times the initial condition. And note that for the calls we have to go from 0 to infinity, and for the puts we have to go from minus infinity to 0. But when we do that, we have the solution of the heat equation right there. Right? We just need to multiply with these payout profiles with these initial conditions. That gives us the solution directly. And we see the call formula here and the put formula in a few seconds. So I think these expressions are fairly big and we want to use them in a moment on a lot of computation, so it makes sense to C-compile them. So we use compile with the option compilation target goes to C. So I just did a copy paste here of these two solutions, and I store them away as compiled functions in BS call compiled and BS put compiled. So let's look at them. We see that this looks the way we would expect this for a call and a put. We can modify these parameters here. Really, sigma is quite relevant, and of course the time, right? We get something crazy and wacky when we go to extremes, but generally this looks like a call. It gets even wackier for the put when we change these parameters. Look how this is bending downwards here to the left, and how strongly this depends on the volatility. But we see several characteristics that we would expect. For example, we come down to 0 at the strike as the time goes down to 0. Reminder, tau is time, and we see really this kink here when we have tau as 0, and it's getting smooth as tau gets larger. So I think intuitively this looks fairly good, as we would expect. For the next steps, we need some more substitutions or back substitutions. We define this substitution, calling it V for the call, and with this we can now compute our call price formulas. And there are several ways to write them. They're all equivalent. I show you 5 ways to write them based on how we simplify, right? You see that in these 5 versions, the only difference here is how we simplify afterward. And here's a trick. If you really can't get good results in your simplify or full simplify, then throw a power expand in front of it. I've counted it several times that doing a simplify after a power expand or full simplify after a power expand gives amazing results. It's quite useful, I think, to try a power expand before you do a simplify or full simplify. Okay, so here are 5 equivalent versions, whichever you want to use, whichever fits better for your computer system. And when no dividends are paid, this reduces to simpler formulas. I show you 3 versions here. You see that we're using R here twice in the second argument. So we are getting the simpler formulas when we don't have any dividends, which is the case for most companies. Most companies in the United States don't pay dividends. And now it really looks as we would expect, right? Let's change the time to expiration. Long time we get a smooth white curve. Short time to expiration we're approaching the kink at the strike, right? I have the 80 strike here, and the interest rate doesn't make much of a difference, but the volatility does, right? Small volatility and small time to expiration really gives us this hockey puck, no, not hockey puck, this hockey stick curve, and larger volatility and larger time to expiration give us smoother curves, almost like a straight line. Okay, we do something similar for the puts. We perform this substitution. Let's look at it with a simplify. When no dividends are paid, we get an even simpler formula, and this would behave as we would expect. Let's look at the puts. Again, let's look at a king for low T and low sigma. We get this king at 0, and for larger values these things get smoother and the rate makes almost no difference. And we can even verify that these call and put formulas are correct. Let's do another shortcut. Instead of call, let's call it CV and only of 2 variables, T and S, and a shortcut for the puts. Let's start with A and PV of only 2 variables. And if we perform this replacement, do we get an equation that is true? And yes, that is the case. We started out with BSPDE 1, and after we replace the value of the derivative with the call formula and the put formula, we get true. So the equation is valid. Okay, so we completed the round trip. We're done now. And we now understand that the BSPDE and the heat equation are just transformations of one another. We need several substitutions, but as long as we keep track of them, we are able to transform one into the other. We can do a complete round trip. Okay, next I'd like to make a couple of comments on the interest rates and the dividend rates, because they seem to be distorting the entire picture a little bit. We should hone in on some of the local behavior of the European call and put prices and compare against the payout profile. So in this example, I want to amplify the situation a little bit, a huge plot and huge interest rates. I'm using 25% interest rate. Now that is not realistic, but that doesn't matter in order to study the robustness of our formulas. So what we see here is that the European put price, and that is orange, at some point in time undercuts the payout profile, that is the red curve. But it doesn't go down all the way to 0. There is a lower limit, and that lower limit is the discounted payout profile here. I am taking the the interest rate, and I'm discounting, I make it negative, so it's minus 25% per month, because that's the time horizon that we have. I've set 1 month here, and I multiply that with our strike 80 before I subtract S. So this is our lila curve here. This curve that we see in lila, and we see it's a lower bound for the European put price. And we see that the European call price, the blue curve, also approaches the payout profile, the intrinsic value, right? Strike minus spot and spot minus strike are called the payout profiles and the intrinsic values. So we see that blue approaches green, but it stays above. And we see that orange undercuts red, but it stays above lila. So these are actually very different behaviors. The European put price, as S goes towards 0, and again, that's extreme, right? If a company has a stock price value of 0, there are no assets, we don't have a company. But we see that they have the same value. So as the stock price goes to 0, the put price, the European put price, is actually not the strike. It is the discounted strike, right? It's 80 times this exponential function here, right? Minus 25% taken for a month. We get the same value here, right? The discounted strike is the same as the European put price in that limit, only in that limit case. But we get a different story for the calls, because for the calls the dividend rate is relevant. So here again, this is an extreme case, right? I'm not saying 25% interest rate is realistic. That may have been in the late 70s, but definitely is not realistic now. We see that the blue curve now cuts under the green curve, but there is no lower limit. Well, 0 perhaps, but there's not another curve from that is based on a strike price that would function as a lower limit here. This difference between green and blue will get bigger and bigger and bigger. And I think I show this here in this plot, where I let the stock price go really large, like $1,000 now, right? You can clearly see that the difference between the intrinsic value and the European call price increases with the stock price in the limit, and it goes to infinity. There is no limit to it. So these behaviors are not the same, right? Note that the blue curve goes lower and lower without limit other than 0 from the green curve, and in the put case there is a lower limit, namely the discounted strike price. Next, I'd like to talk about the relative dynamics that we have with option prices. And I think of this as leverage. What's important here is that this is leverage, and sometimes it's called relative dynamics. I think of it as a leverage, and leverage is sometimes abbreviated with either lambda or kappa. We're using these Greek letters for it in option pricing theory. So we'll start with our simple stock price SDE, and we use an Ito process again. So let's use an Ito process that we have met in our last session in order to generate stock price trajectories and correspondingly also our option price trajectories. So let's take 1,000 steps again. Let's take 1 year over 1,000 for our time stepping, that's dt. And I'll also set 5% rate for the appreciation or interest rate. We set somewhat arbitrarily 40% volatility. We start with a stock price of $100. And here we see our stock price evolution, and note that after 1 year the stock price ends at 110, right? We start at 100, and in this particular example we end at 110. Okay, let's make a note of this difference. It's $10. And for our option, we also specify we have a strike of 100. That was our starting stock price. The same 5% appreciation, 40% volatility. And now let's look at the call and put prices. And you will see that the calls end up after 1 year at $10, and the puts have become worthless. Right? You see that we have absolutely no value here. The puts end at 0. Well, that's not surprising, because if the stock goes up, then the puts end worthless below the strike. And at the terminal condition for a call, we get S minus K. And if the stock is 110, the strike is 100, we get $10. Right? So the terminal condition here is these $10 that we have seen here, 110 minus 100, and the stock price. Right? We get this difference as the call price. The difference S minus K. That's the terminal payout for a call option. And in the next plot, I just want to show you those together. This is not much different from the 3 plots before, just in one plot. So here you see that the stock goes from 100 to 110. That's equivalent to the call price, the $10, and the put is worthless. So let's do this exercise again. Maybe we have something that ends below. Yes, we do. Okay, so here we have a stock price that ends about, what is it, $81 or so, right? We start at 100, we end at $81. So the stock lost $19 during that time. And we should now see that the put ends around $19, and we have that here. Okay, it's not quite 19, right? But we see the calls are worthless because the stock ended below the strike, and the calls are something like $19 here. Okay, it's not $19, it's actually more like like 79 perhaps. Okay, I can't really quite see this at the end. Let's maybe do it again. Maybe something where we can see it clearer. Okay, I call this $85. Okay, the strike, the stock price ended at $85. So that's 15 below strike, and we see that the put ends at $15 and the call ends at 0. Okay, let's put them together in a plot. We lost $15. That's the put value at the end. Calls are worthless. And in the next plot, I want to show you the leverage. So when we divide by the initial starting price, so here for the stock, here for the call, here for the put, right, then we start at 1. That's the ratio to the initial price. Obviously now that's 1. And from $100 to $85 is a decrease by 15%. So we see the ending stock price here is at about 85. Yeah, this is 0.85. But look how fast the put went up. The put price was much more, and the call ended up at 0. Let's see if we're lucky. Maybe we can get more on a percentage basis. Let's maybe get something that appreciates a lot. I want to show some good leverage. Yes, here's a nice one, right? We start at 100 and the stock ends at something that looks like maybe 145. All right, so that's $45 higher, and we see the call is about $45 now. The put is worthless. In one plot, right, from 100 to 145 means $45 on the call, worthless put. And in terms of leverage, look how high the call price zooms up. We can see that it's above 2, right? The stock price increased by 45% and the call price by much more. Yes, so let's do a plot range goes to all, and now we can see the full extent of the call price movement, and we see that it had a leverage of about 2.5, right? So that means the option price changed by a factor of 2.5, right? Much more than the stock price. All 3 of them start at 1, right? But you see that the orange curve is much more sensitive, much more responsive compared to the blue curve, right? This is the leverage. Leverage is that ratio. So that means you want to be really careful on how many options you buy, and the option multiplier is usually 100. That means one option controls 100 shares. So with that and the strong leverage, you can see why option prices fluctuate so heavily with stock price movement and also with volatility. Right? They go up and down very fast because the leverage can be so much higher compared to the simple leverage of the stock. The stock has a leverage of 1. Okay, next I want to derive a very important equation, and that is called the put-call parity. And I have to emphasize that the following is only true for the European put-call parity. The American put-call parity is much more difficult. It is algorithmic. It's not just a simple formula. So the following is only true in the European case, where we get a very simple equation. Early exercise for the American options makes it much more complicated. So let's say we have a portfolio where we have a stock, and against that we have a put. Again, a protective put, as we started at the beginning when we started deriving the BSPDE. So we have one stock and we have one put against that. That's our protection. That's a protective put. We protect against the downside. But this put will cost us money, all right? Like whenever you buy insurance, you have to pay the premium. How do we get the premium? Well, one way would be to sell a call at the same strike price. And that will give us the premium that we can then use in order to pay for the put that we bought. So we are short the call at this point, right? Our portfolio is long the stock, long the put, short the call. This is how we define our initial portfolio that we have. And now we want to replace the call value at the terminal condition, at the expiration, which is now simply S minus K for the call and max of 0 and K minus S for the put. This is the equation at expiration, right? At the expiration, the call and put price are our terminal values. So it's these max formulas. Let's do a simple transformation here. The max of 0 K minus S is the same as minus the minimum of S minus K. So we are getting this formula. This is just a transformation. There's no rhyme or reason to this other than the transformation step at this point. And with that, we are now able to rewrite this formula and replace the max of 0 of something and the minimum of 0 something with that value itself, right? The max of 0 and A plus the minimum of 0 and A is A itself, right? That's just simple math. And we're now getting a formula that I think is probably more complicated to read than it should be. If the strike is the same as the stock price, then the portfolio value is K. And if the stock price is the same as the strike, then we take S. But it's also K because they are the same, right? If they're different, it's K. If they're same, it's S. But as they're the same, it's also K. So I filed a bug report why this is not simplifying. I think mathematically it's entirely correct, but we're after a simplification, right? The goal of simplify is to get an expression that has a lower leaf count. So I don't know why this didn't simplify. For all practical purposes, this is K, right? Because if K and S are different, it's K, and if they're the same, that's also K, because it's S and S is K. So that means at time t, the value is K. But that means the value of the portfolio at time t is not random, but it's deterministic and constant. That's the strike price, right? It's K. But that means the value at any point in time before the expiration is simply the discounted strike price, right? What else is it supposed to be? If something has a certain value 3 months in time, then the value that is predetermined. We know it's going to be k. It cannot be anything different. Then right now the value has to be the discounted value of k. So all we need to do is compute the present value of the strike. So all we do is take k and we discount it. And again, that is by multiplying with e to the minus r. Note that for the net present value, you need to take the negative of the interest rate. So this is what we have as the value of our portfolio right now. It's going to be k in the future, but it's this expression right now. So this means at time t, we have a portfolio value that is represented by this value. We simply set them equal, right? This k times the discount factor is the same value as our starting portfolio. Remember, this was S minus CV plus PV. So we set them equal and we get this equation now, and we rearrange. All we do is that we subtract S on both sides, and at that case we get call value minus put value is stock price minus discounted strike. And that's very easy to remember, right? Call minus put is stock minus discounted strike. That's the put call parity. And that's the European call parity, not the American call parity. So the difference between the stock price and the discounted strike increases with interest rate and with time to expiration. And we see this directly here in the formula. In order to make this difference big, we would need large interest rate or we need large time to expiration. So right now we have very low interest rates. In fact, in most Western countries we have negative interest rates. And with low interest rates, the relative factor really is the time to expiration, right? And then we have this difference as the same as call minus put. Okay, so this is the way to remember this. Call minus put is stock minus discounted strike. And I emphasize this is only true for European options. But in real life, the difference between the European put call parity and the American put call parity is not all that significant, especially when we have low interest rates, as only the interest rates make a difference here in the European and American stock pricing. All right, so that's the put call parity. That's an important equation to remember. It allows us to compute a call when we have the put price, because we always know the stock price, we know the interest rates, we know the time to expiration. So it's one way to compute the calls from put and stock price, or the puts with call and stock price, or even the stock price. When we have call and put value, we can also compute the stock price. So in this equation, you can basically rearrange it to whatever you want. But call and put of the same strike always have to be seen together. And that's why this equation is so important, because it brings call and put together and we can compute one from the other. All right, next I want to look at the sensitivity analysis parameters, and they're called Greeks. In option pricing theory, they're called the Greeks. So in order to properly manage an options portfolio, we have to be able to quantify how the value of the portfolio changes with respect to any changes in the input parameters. So we're interested in things like the first derivative, the second derivative, with respect to the stock price change or the change in time, the time to expiration, because all of these financial derivatives depend on the time to expiration. So we're looking at these first and second derivatives. And in option pricing theory, they are usually named with Greek letters, and hence we call them the Greeks. So let's start with delta. So this is the European call price formula, and we take the first derivative with respect to the stock price. That is called the call delta. And the same for the put delta. So I just take the European put formula, differentiate with respect to the stock price. That gives me the put delta. So these are these European formulas for that. and I simply take them and compile them to C. I want to compute with them in a moment. I want to plot them. So I simply take these outputs, this one for the call, do a copy paste, and then compile it. Here we have the compiled delta for calls and puts as C compiled functions. So let's plot them. Let's look at them. All right. So here we have them, and let's plot them. And again, let's look at short times to expiration, and let's look at small volatilities. And you see this jump here that we saw earlier. It's 0 on one side of the strike, it's 1 on the other side of the strike. And this smoothens out with larger times to expiration or larger volatilities. The parameters A and B don't really make much of a difference here. I can change A and B and we don't see big changes. It's not very rate sensitive, but it is, of course, very sensitive with respect to the time to maturity and the volatility. All right, so these are call data and put delta, and you will notice that they look the same, and they really are the same, except that the put delta is the call data minus 1. Right? You see that the call delta we go from 0 to 1, and the put delta we go from minus 1 to 0. This is the natural consequence of taking the derivative. You will remember that we had the hockey stick curves. So if the hockey stick goes to the right, you have a derivative of 1 on the right side. If the hockey stick goes to the left, you have a derivative of minus 1 on the left. And this is exactly what we're seeing here. So you can think of the put delta as the call delta minus 1. And this is not entirely true for the American options. Now you see that when we take the difference here, right, the call minus 1, and take the difference to the put, we get 0. Right? So a European call delta is the same as the put delta, except we have a minus 1. We have to subtract one of them. So put delta is call delta minus 1. In the American case, it's very similar, but not quite the same. And the second derivative is called gamma. So when we take the call price again here that we had before, and we differentiate twice with respect to the call price, then, I'm sorry, with respect to the stock price, we get gamma. So the second derivative with respect to the price is gamma. So here's a call gamma computing, a put gamma computing, and let's see if they are the same. We see that that is the case, and that is really not too surprising, because the first derivatives, that was delta, only differs by 1. So these curves, although they are different because they're shifted up down by 1, they still have the same shape. So if they have the same shape, then another differentiation with respect to the price makes no difference, so they are the same. So let's compile them. So let's look at them in a plot, and I'm only showing you one because call and put gamma are the same. So we see that it gets pretty spiky around the strike for short time to maturity and for short volatility. Well, not too surprising, because we see this jump here, right? If you take the first derivative of this, what do you expect? Why would this not be a jump, right? This is clearly a jump here at the strike, and we see that here in the second derivative. And it smoothens out for larger times to expiration and for larger volatilities. Okay, so this is gamma, also a very important Greek. Now the next derivative I want to show you is called theta, and that is the first derivative with respect to time. Okay, you see that I'm differentiating this formula with respect to t. I do it for the calls, I do it for the puts. I take these formulas and compile them because I want to have a call theta and a put theta, and this computed pretty quick. And here are my two compiled functions. So let's put them, and we see that call and put theta are not the same, even in the European case, right? That is because the difference here is an interest rate argument, because buying the stock means you get the asset, but you lose the money, and when you lose the money, you can't earn interest on it. When you sell the stock, you lose the asset, but you get the money back, and when you have money that comes in, you can put it in a bank and earn interest. There's no interest on the stock, there is interest on cash. So let's look at this. Let's look at this theta. And here I want to point out that we really can get some very wacky behavior depending on the stock price and depending on the time to expiration. We can get very wacky formula here, and also the time dependence I'll show you in another plot later. We simply get different behaviors for calls and puts. You will see that the curves are not the same, but they are negative when you own the option, and this option pricing formulas are seen from the perspective of the buyer. So when you own the option, then you're short theta. That's called short theta, because as you hold the option and time decays, then the option price loses value. This is true for calls and puts, right? When you buy calls and puts and assume for a moment that nothing changes, the stock price doesn't change, the volatility doesn't change, then you lose money on these calls and puts because they are diffusing out towards the pair profile. You have seen that the plot I showed you earlier has the call and put prices above the payout profile. So they decay as time moves towards the expiration. The calls and puts lose a value. That means if you're short them, then you get money for it. Your short calls and short puts suddenly bring you more value in your portfolio. So this is somewhat similar to the perspective of an insurance company. You pay them the premium, and the amount of time during which you're insured goes lower and lower and lower. And the insurance company is like the short option position. They are the sellers of the option. They get your premium, and hopefully they don't get assigned. Hopefully they don't have to pay for the insurance case, right? Like your house burns down, or they have to pay out on your health insurance, right? Insurance companies like to cash in the premium and hope they don't get assigned. You are the buyer. That means you pay the premium and you lose the money if nothing happens. You still have the coverage. It's not a total loss because in exchange you got the coverage. So the money is not lost, but the money is eventually gone without any money, any financial payment you got in exchange after the insurance period has lapsed. So you are short theta if you buy. If you're the buyer, then you are short theta. These numbers here are negative. And no matter how we change this, this is always the case. It's always seen from the perspective of the option buyer or the long position. And usually option traders like to divide this annual theta into a daily theta. So we get the same curve. We just divide this by 365. This is basically just a rescaling. It's the same curve except the y-axis has changed now because we now have a daily theta as it is called, right? It's just the same thing divided by 365. Okay, it is the same plot as the previous but scaled by 1 over 365. All right, another Greek now would be rho. So we take the same formula and we differentiate with respect to R, the interest rates. This is called rho, and it describes the sensitivity of your option with respect to changes in the interest rate. Again, let's compute them, and I want to plot them, so I'll also compile them. I here have my call rho and my put rho, and they are not the same even in the European case. If we let this comparison compute out, where we want to see if they are the same, we will see they are not. And again, the reason is an interest rate argument. You will get a discounting factor here as the difference. And we see this simplify expression will tell us that they are not the same. You will see that we have a discounting operation here of the strike times the time difference, right? This is the time to maturity. All right, they're not the same, and the reason is the interest rate argument. Okay, so let's plot them, and we're getting a constant number here. Okay, that depends on my parameters here, and is constant, right? This is a constant number, and also here we have a constant number. Okay, so let's plot them, and here we have the call row and the put row together. I think I have this wrong here. This must be called row, and this must be put row. And we have them here, and we see that they somewhat resemble straight lines and can change their shape a little bit, but basically row is not all that important for most traders, most stock option traders. So let's look at some row values here. And again, a big impact are time to expiration and the volatility sigma, right? They have the biggest impact. And keep in mind, when we're having these numbers here, these factors on the y-axis, this would be relevant for 100% change, right? 100% in interest rate, that's enormous, right? So here you would also have to divide by a factor, because this derivative was taken with respect to 100% change, which we don't have, right? So you have to take these large numbers on the y-axis with a grain of salt. These numbers get huge if you assume 100% change, but we don't have that. Interest rates are low and they change in very small increments. Okay, the next Greek is Vega. It is called Vega. Note that this is strange nomenclature because there is no Greek letter Vega. So here again we take the call option price, we differentiate with respect to sigma, we do it for calls and we do it for puts, and I want to plot them, so I want to compile them. And Vega is a very important number because the option prices are very, very sensitive with respect to changes in volatility. I had already mentioned this at the beginning. Vega is a number that is very closely monitored by options traders. They have to know how sensitive their options positions are with respect to changes in volatility. Call and put Vega are the same, right? We get the same formulas here. This call and put formula are identical. Okay, so let's plot it, and here note how large Vega can get. For 1 year, in this case, we have almost 25 as a maximum. I've had already played with this a little bit. So let's set T to 1 year. Yeah, we get big numbers here around 30. And this shows you how sensitive the options prices are with respect to volatility changes. Now again, this is with respect to 100% volatility change. But given that volatilities for stocks are usually between 10% and 90%, this is a big deal. These are large changes that we have. So Vega itself is very sensitive with respect to stock price and time, and Vega itself then is a large number. All right, so very important for options traders to look at. Volatility is a very important determinant. These are high numbers here on the y-axis. And I think we probably understand Vega a bit better if we look at it in 2 dimensions. Again, note the large numbers on the y-axis, and we see this as a surface that is somewhat rolling down towards the expiration. Right? As time to expiration rolls down, our vega comes down towards 0. And that's just understandable, because when there is not much time to expiration left, then you don't have much time that changes in volatility still have an impact on your portfolio. Right? That's why with time to expiration, vega rolls down. Not necessarily the volatility, sigma, but the change in volatility. Change in volatility needs time. And as we take down time towards 0, the change in volatility comes down. Not necessarily the volatility itself. A stock can be very volatile all the time. It doesn't care about an approaching expiration. In fact, very often stocks get extra volatile as a big important expiration approaches. Right? Stocks can be very volatile just one day before expiration or on the expiration day due to the expiration. Right? The expiration itself can be the reason for increased stock volatility. There are several names for that, and there are several scenarios for that. One, for example, is what's called caught in a short situation. If you're short a position, you now owe money, or you have to buy the stock. Well, how do you do that? Well, you have to buy the stock now, because you have to deliver the stock. You're short the stock, so you have to deliver it. So how do you get it? You don't have the stock. You have to buy it. So now you have to buy. But if a lot of people are doing that, then a lot of people have to buy the stock. But if a lot of people do that, that increases the stock price. So more people have to buy, which increases the stock price, which makes it more expensive for them. So that increases the stock price because so many people are caught short, right? So now they have to buy it, which is totally against their interest, because you don't want rising prices when you have to buy it. But it's the fact that so many have to buy it that increases the prices, which only makes it worse. That's called a short squeeze, when you're caught in a short squeeze. So here you see how vega itself is dependent on sigma, the volatility, and you see that change is not all that big, right? There is not too much change from left to right, except really near 0. But when volatility is 0, all these option pricing models break down. When you have low volatility, well, then the change in volatility is also very low, quite understandably, right? But the vega also rolls down with time to expiration decreasing. Okay, so this is vega, very important Greek. And I want to point out that there is no reason to look at the Greeks only by looking at the change of the Greek with respect to the variable that was differentiated. Why do we have to look at my delta only with respect to stock price, or my theta only with respect to time, or my vega only with respect to volatility? Right? There are these vegas, these Greeks also depend on other parameters, and here I've shown you the vega as it changes with respect to the stock price, even though stock price is not the variable we used for differentiating it, right? So we can look at delta by price, gamma by price, rho by rate, theta by time, vega by sigma. And that's just fine, and they're definitely important, but it's very important to also look at these Greeks in terms of all the other parameters that determine them. The last plots, I think, make clear that they all vary with all parameters. Again, here I show vega with respect to changes in stock price. And sometimes it's important to look at 2 or 3 independent inputs to understand the characteristic behaviors. Okay, so let's now look at the theta. And theta, as I had mentioned, means from the long perspective, you're losing on theta. as expiration approaches, the call and put values go down in value because you have less time for volatility, less time for change. There is simply not much time left as you approach expiration, during which you can still see major changes in volatility or changes in stock price. So the time value, and this option price minus intrinsic value, comes down, and it predominantly comes down at the strike, and we've seen that in the plots above. The largest difference between the option price and the intrinsic value is at the strike. So here at the strike of 80, we can see that theta literally craters. It really craters down to a very negative value. Again, I emphasize theta is negative, and it just craters down at the strike because at the strike is where you have the largest amount of time value. In the wings, the difference between the options and the intrinsic value becomes smaller and smaller. Okay, so we absolutely crater here at the strike. So let me change the threshold a bit to show you that we have a valley coming into the expiration, and with larger time to expiration we have more of a flat surface, but nearing expiration it absolutely craters. And theta is also dependent on the volatility. If there is not much volatility, then it gets even more spiky near the expiration, but less pronounced before the expiration. And with larger volatility, we see that everything is a bit more smoothed out as a surface. All right, so this is theta and plotted with respect to the volatility sigma, again, which is not the variable it was differentiated by. All right, so for the next topic, I want to show you time-dependent Black-Scholes formulas. So we can make our option pricing even more powerful if we allow the parameters to be time-dependent as well. Who says that volatility or interest rate or dividend rate have to be constant numbers? That's not realistic. And as long as we're only changing them with respect to time, we're in good shape. As we've seen above, we can compute the expectations and means for continuous functions with an integral. So one way to deal with this is that we can allow functions, for example, a of a time variable or b of a time variable or sigma of a time variable tau, and then we can use the integral in order to compute the expected value for them. We can use integrals to average these functions. So I call it the generalized Black-Scholes PDE. I call it BSPDE. And here note that we have them as time-dependent functions. My sigma is a function of time. My a is a function of time. There's a b of function of time. So we can simply say that we allow a time dependence for a, time dependence for b, time dependence for sigma. And when we integrate them from t to t, then we are averaging them and we are creating an expected value. And those are the numbers that we can now substitute. So we can compute a general call and a general put simply by taking our call and put prices and applying this substitution with the integrals. This gives us new formulas, and in these formulas you see that suddenly we have these time integrals, right? Here's a time integral for b, here's a time integral for a, here's a time integral for the volatility. And if we simplify that a bit, we use a shortcut GC for the general call, and a GP for a general put, we have these formulas for our call and put prices. I just want to use the shortcut here. It's really the same formula, but for the next things I want to use these shortcuts. And in the next step, let's actually make them functions of time. So let's make A, B, and sigma functions of time. And for example, here I define them as parabolas, right? Polynomials of second degree, that's called a parabola. And these coefficients of the parabola could come from, for example, a curve fitting or a regression. Maybe you have data, maybe someone published data, maybe we are able to do a polynomial fit of second order to a time-dependent volatility. Maybe we have that for the interest rate or the dividend rates, right? The advanced firms, they have all sorts of model in which they're trying to predict volatility as a function of time, dividends as a function of time, interest rates as a function of time. So you could conceivably do a curve fitting, you could do a regression, and let's assume you are using a second order polynomial. So here we have sigma as a second order polynomial, dividend rate and interest rate. And in that case, if we use these functions now, and you will see here I use the parabola for the rate, for the dividend rate, for the volatility sigma, then we are now getting a call pricing formula that has exactly these factors, these parameters in these formulas, right? So we have R0 in here, we have R1, we have R2, and we also have a sigma 0, sigma 1, sigma 2, right? So these factors that we have from our fitting polynomials now come directly into our pricing formula. And just for kicks, I am using trigonometric functions in the next example. Here as well, the parameters for the functions could come from a curve fitting or a regression, and we can now create a call function with these parameters that we get from a curve fitting or a regression. It's the same in principle, right? There's no rhyme or reason. In the first example, I used parabolas. Here I'm using a trigonometric function, and yeah, I use sine for A and B, and I use a cosine function for the volatility. So these are arbitrary functions. These are crazy functions I picked here. I just want to show you that you can use your fitted model to use in your call and put pricing formulas. The same is true for put. I'm just not showing it. But it is important that all this must be a time dependence. This would not work when we are using a dependence on the stock price. It has to be restricted for a time dependence. If we want to make the parameter dependent on the stock price, we have to resort to numerical solutions of the PDE, and we're going to do that later. But the time dependent case is relatively easy to cover. Okay, next I want to show you that we can speed things up massively with CUDA. So I first need to make a point about the shortcomings of the European options. I've emphasized it before, we're dealing with European options here, not American options. And most exchange traded options are American options, which we haven't dealt with yet. And for the American options, we really have to resort to algorithms. There are no simple formulas available as these formulas we're looking at here. However, the European option pricing formulas are not worthless because they can still be applied in many cases. For example, to price dividend-free call options. Most stocks pay no dividends, and therefore the theoretical extra value of an American option for early exercise really has no value. it's there, but it has a value of 0. But then that means the American option can be priced as a European option, right? Every dividend-free call is also a European call. The early exercise value is 0, and keep in mind this is half of most stock options, because we have calls and puts, so the calls are 50% of it, and really just a small percentage of stocks in the US pay even dividends. So this is quite a speed up if we can price dividend-free American calls with these formulas. The same is not true for the puts, only dividend-free calls. We look at that later. So let's load the CUDA link package, and I prefer to use my GPU 5 simply because it is the coldest, the coolest that I have. The GPU 5 is 30 degrees, or the other ones are warmer. The fifth GPU that I have has the best cooling. So we have Black Scholes in the support files. This is very useful that we have this right there in our Mathematica installation. It makes it extremely convenient because now we have European option prices directly at our fingertips, ready for CUDA. So yeah, on Linux, the CUDA function load has to be loaded twice, and I have to provide the compiler installation. I want double precision. My GPUs 2 through 5 are Tesla cards, so I want to have double precision. Number one, we really want precision when we're talking with option prices. There's too much at stake when we're dealing with the financial markets. And the Tesla cards are absolutely great in terms of double precision. So for comparison, let's compile the call and put prices again. This is just for comparison. And I use tuples to generate a very large number of option prices that I want to compare. So when I take spot prices from 70 to 90 in steps of a cent, I take the strikes as 80, 81, 82, 83, 84, 85, and I take expiration times from 1 hour to 1 week in steps of 1 hour. Then I get 672,000 options. So let's compute these prices with our compiled function. It takes much longer, but still, due to the compilation, it's not the end of the world. We just took a few seconds to compute. And keep in mind, we have to multiply this number by 2 because we are doing calls and puts. We're really talking about 1.3 million options here. Okay, so for the CUDA version, I define a function compute, which first allocates memory on the GPU, one for the calls, one for the puts. I take my current prices vector, my strike prices vector, my strike times vector, and the function will now compute them as an outer product. And we use vectors for stock prices, for strike prices, and strike times. This is normal. This is how we are computing these things in a real trading system. And things like the risk-free rate, they don't change a lot. And if they do change, we have to recompute the entire portfolio. So in this function here, we are simply using this as one variable. We're not providing a vector. And for volatility as well, although volatility changes a lot and frequently, and in the following, I'm also going to loop over this. We also really want to have a vector of volatilities. But with this function compute defined now, let's compute this. And it took us 370 milliseconds to compute these 1.3 million options, right? 370 milliseconds, much faster than what it took us here to compute them with our C compiled version. And in the next cell, I simply look at the differences, right? So I'm subtracting the flatten of the exact calls and the flatten of the exact puts. And we see that our minimum value has 4 correct decimals, the max value 4 correct decimals. The maximum absolute difference is the same as the max, right? Obviously we have the same number here, 4 correct decimals. That's pretty good. And when I total them, then I really get numbers that are not zeros. But again, given that we are talking about 1.3 million options, I think these are errors that are acceptable. The maximum errors here have 4 correct decimal. It's the totalization that really makes these numbers fairly large here. Okay, so look at the memory information. We have 672,000 calls, 672,000 puts. That's a large byte count number here, but the point I'm trying to make is that we can trust this formula, all right? We trust our own formulas, and we see that they match the CUDA version that we have in Mathematica. So these numbers match. We can trust both of them. We can trust the CUDA version. We can trust the C-compiled version that we have developed. So in the next example, I want to show you that we can get the expected behavior, the expected shapes that we have similar to the plots that we have computed above. It was very fast to compute. It took 22 milliseconds, and we get these option prices as we would expect them. So here with this one, we're looking at 1 day to 7 days before expiration in steps of 1 day. And we are getting these 8 curves here, right? We have 7 colored curves, and we have the black curve that is the payout profile or intrinsic value. So when we look at them, we really get what we would expect. And let's use hourly time progression here. We're getting closer to expiration now. We need 30 milliseconds, and we now have much more in terms of our times. We see that we have many more curves here because we are counting 1 day hourly. This is 1 day hourly. And we next look at a quarter year down to 1 day in steps of 1 day. Right? 3 over 12 is 1/4 of a year plus 1 day. So we have 182,000 tuples. That's 364,000 options. We computed in no time. Okay, 147 milliseconds. And let's look at the spot prices that we have here in these plots. And you see quite a lot here, right? This is 90 or 91 days. 1/4 year in terms of days is 90 or 91 days. So we have 90 or 91 curves here for each. I think sometimes it's instructive to look at the 3-dimensional plot and a contour plot. I've already done this because it takes a while to render. Yeah, the time, it's the same computation. I won't do it again, but what really takes like a minute or two here is rendering this in the Mathematica front end, not the computation time, it's the render time. Okay, so here we see our call surface. It's a bit pointed here when we have short time to expiration. It's smooth when we have longer time to expiration. And the contour plot reflects that. And I usually like to look at such surfaces in what I call a mesh, and we can understand the behavior much better when we are creating these mesh plots, which we simply generated by going very dense in one dimension and not dense in the other. Right? This is fairly zippy here. We have a fairly zippy interactive experience here, and we can change our perspective here much faster and much zippier than this 3D plot that we have above here. When we do this as a dense mesh, like meshing goes to 100, this takes quite a while. So you have to set this up by using very dense point in one directions, but not in the other. I think this is usually much easier to understand. Of course, we can reverse the density direction. We can also make the time variable dense here and keep the stock prices wide. So we have these meshes here in this plot, and this also gives us a good idea of how this surface behaves. And I love the contour plots. Again, they take a while to generate, so I've already done this. The contour plots also tell us quite a lot about how these surfaces behave. So now let's specifically do a timing result, because I want to show you just how fast these formulas are when we are using CUDA. So let's generate a lot of tuples again. So we're going from $70 to $90 in steps of 25 cents. We're going from $90 to $70 in terms of the strikes. And time-wise, we go from 1 day to 1 month in steps of 1 day. So this would be 53,000 tuples or 106,000 options. And look at the timing result, because what I now want to do is that I compute with different values for the volatility, right? The volatility in this setup for the CUDA computation is one parameter. It's not a vector, but by looping over it, I can treat it like a vector. So volatility, I go from 10% to 90% in steps of 1%. And then this is what I call with the loop variable I in compute. And when compute is done, I can do CUDA memory get operations on the calls and the puts, and I store them away in variables called core results and put results that depend on the volatility and not the timing result. This should be like 5 seconds or so. This goes fairly quick, yeah, 4.2 seconds. And I generally like to do timing results with a comparison with the speed of light. So for example, in this calculation, light travels less than 500 feet for the average per option computation time, right? If we divide this timing result, those 4.2 seconds, by 91, because we had 91 volatility steps, by the length of the tuples, by 2, because we have calls and puts, and then multiply with the speed of light measured in feet per second, we are getting the number of feet that light travels per computation of one option, right? This is the average per option computation time. So I think this is a quite remarkable timing result. It shows how fast we can be when we are using CUDA for the pricing. And I also want to point out that I don't even have good GPUs on my system, right? My GPUs are definitely not state of the art anymore. The GTX 980 is not state of the art anymore, and the K80s that I have are not state of the art anymore. So with really equipment that's something like 5 years old, we can get remarkable timing results here. And again, I like to do timing results by comparing the time to speed of light distance. 500 feet tells us something about how fast the computations were. Okay, so we're done with this. Let's unload the memory. And I also want to show you that it's relatively easy to plot the Greeks or to compute the Greeks when we are using CUDA. So here I use a symmetric centered first difference to compute the first derivative. And you remember from high school, that was f of x plus a small step to the right minus f of x with a small step to the left divided by 2 times the step size. So here I use 1 over 1,000 as a step size, and I'm adding 1 over 1,000 to every stock price. Right, so the spot prices I store away in T, and then I'm adding a constant array to T. The constant array is 1 over 1,000 that I'm adding. Note this plus sign here, so I'm adding it. This plus sign here is this plus sign here from the formula. Okay, so let's define these tuples. Let's compute them and let's retrieve the result, and I store them away in calls plus and puts plus. This is the first expression here, f of x plus h. Right, this was now done for something like 368,000 options. So now I have to do it for the other term, f of x minus h. So I now compute this by using a constant array that I subtract from the spot prices. Right, note that here I'm saying minus constant array. So these are now my tuples for the second computation. Let's compute it. It took 12 milliseconds. Let's retrieve the data and store away in calls minus and puts minus. So now let's compute the actual deltas, and I store them away in call CUDA delta and put CUDA delta. So this is calls plus minus calls minus, just like we have here. We have a step size of 1 over 1,000. 2 times that is 2 over 1,000, and instead of dividing by 2 over 1,000, I can simply multiply with 500. All right, so let's plot these, and we see the typical behavior that we have already seen earlier for our delta. It's 1 above the strike, it's 0 below the strike for the calls, and we see those square root shapes here in the contour plot. Takes a while to render, so I had already done it, but you've seen how fast the computation is. It's the rendering that takes so much time. Okay, well, how about theta? That is the first derivative with respect to time. So let's compute our thetas in a similar way. Let's add a constant array with a step size of 1,000 for calls plus. Let's do the whole thing for the steps to the left. So we are subtracting the constant array of 1 over 1,000. Let's generate the tuples. Let's compute it. Took us 11 milliseconds. Retrieve the data and use the same formula, plus minus minus times 500, stored in call CUDA theta and put CUDA theta, and in the plot we now see what we've seen before, that theta is mostly a surface, but as time to expiration goes towards 0, theta craters at the strike, right? Around the strike we see that theta goes largely negative. But most of the time it's a flat surface. You see in the contour plot that the color is mostly this orange yellow type, but as we approach an expiration you see that it gets very dark here because our theta craters. Again, that's the position of the long option holder. We are getting negative thetas. Okay, so I come to the end of my session, and at the end I want to explain a couple of features that I used that are probably worth an extra mentioning. So let's look at the max of 0 and another expression again. We needed that in order to transform our terminal conditions. So if we make a simple attempt where we have this expression which really should cancel out the k, all right? If we use a factor on this expression, then we really can get rid of k, but it's inside the max. It's inside our max expression here. So we may be tempted to just use a replacement rule where we are trying to use factor on the second argument in the max. And if we do that, then we still get our old formal back because it doesn't eliminate k. Rule doesn't have the hold rest property. So that means when we apply this rule directly, there's no change, right? There is nothing that's happening here when we are using this directly. So when we are applying this to the expression where we want to cancel out the case, we are getting no improvement, right? There is no change on that. The solution is to use rule delayed, and you will see that here we're using colon larger than, right? This is the shortcut for rule delayed. You will remember rule delayed is using colon and then the larger than sign. All right, so if we use this, then we can factor out the second argument in the max function. We can really simplify this. K is gone. And I mean, strictly speaking, we can't even simply use the replacement rule that performs a division of a max expression divided by another expression as performing that division inside the max. We can simply not do that because we could be having negative numbers, right? If we use this, we really want to make sure that we're talking about positive numbers. We have this in the step here where we want to perform the division inside the max. So the problem is that A could be negative. The divisor is A, the divisor could be negative. And we see that when we plot the difference, and the difference between these two expressions here is not 0 everywhere. It's 0 when A is positive, but when A is negative, then we cannot do that. Yeah, I'm sorry, here I'm using K, right? Here I'm using a negative K. It's the same thing when we are trying to divide this max expression by K versus putting it inside, which after putting it inside would give us the simplified version. So A could be negative. In this case here, I'm plotting it with K, same thing. So we cannot simply do that for negative numbers. So the proper way to do this in Mathematica would be to assert that A is larger than 0. The divisor is larger than 0. If we do that, then it is proper to do that division. And the way to specify that is to use condition, right? This is a shortcut for condition in Mathematica, sometimes called just /semi. The Mathematica programmers call that /semi, and it stands for condition. And when we use condition, we can now attach a true-false condition, A larger than 0. That can be true or false. But when we're now asserting that with that condition, then we are declaring that A is supposed to be positive, and then we can apply this rule. And we know that the strike price is always positive. Therefore, performing this transaction, performing this transformation here is a legitimate operation. It was a safe transformation that we did here. All right, because we know that the strike price is always positive. And a really totally super proper way to do that, which combines both things, that is getting the K into the max and then dividing it by K, would be by using up-value definitions. Mathematica is a symbolic system that allows us to make up-value definitions. In this case, we can, for example, make a declaration for a function that I call mymax that specifically applies to mymax. When you use /colon, then the definition that follows applies to mymax. Okay, so that means mymax of 0, b divided by a positive number is simply the max function that uses factor of b divided by the divisor on the right hand side. So this is now a definition that specifically attaches to mymax. And we are also asserting that K has to be positive. This is a definition that now specifically attaches to K, because K is on the left side of this /colon. We're saying K larger than 0 is true. So with this definition, mymax simplified, we can now safely use MyMax Simplified on this expression where we are performing everything together. And you see that we have put the division by k into the max function, and then we have done a factor in order to eliminate k. All right, so this brings me at the end of my session. I hope you had as much fun as I did, and I hope I see you again next time. Thank you. Bye-bye.